It's the most powerful technology of our time. But how does artificial intelligence actually work? We're pulling back the curtain. This is AI Deconstructed.
In our last episode, we explored the second major paradigm of machine learning, unsupervised learning. We saw how an algorithm, given only raw, unlabeled data, could find hidden structure. We looked at clustering algorithms like k-means, which group similar data points together, and dimensionality reduction with PCA, a technique for compressing data by finding its most important underlying patterns. The core idea of unsupervised learning was learning by observation. This stood in sharp contrast to our first paradigm, supervised learning, which was learning from a teacher, using a dataset where every single input came with a correct, labeled answer. We had the questions, and we had the answer key. So, we have learning with an answer key and learning with no answer key at all, just observation. This brings us to the third and final pillar of classical machine learning, a paradigm that is perhaps the most intuitive, the most biologically plausible, and in many ways, the most ambitious. What's the third way we learn? We learn by doing. We learn from the consequences of our actions. Think about the first time a baby learns to walk. There's no instruction manual. No one hands them a diagram of physics and biomechanics. Instead, there's a wobbly, uncertain process of pure trial and error. A random lurch forward, a moment of precarious balance, a small internal victory, followed almost immediately by a gentle tumble to the ground. That fall isn't just a failure, it's data. It's a piece of feedback from the world that says that particular combination of muscle movements didn't work. The brief moment of standing, however, is also data. It's a positive signal, a hint of a successful strategy. This cycle repeats, not just dozens, but hundreds or thousands of times. Each attempt, each piece of feedback, slowly refines an internal strategy, an unspoken policy for locomotion. This is learning in its most fundamental form. It's not about being told the right answer, it's about discovering it through interaction. This is the universal algorithm of learning, hardwired into the natural world, from an animal foraging for food to a human mastering a new skill. What if we could capture the essence of this powerful, intuitive process in a machine? What if we could build an algorithm that learns not from a pre-labeled dataset, but from the consequences of its own actions, driven by a goal and guided only by a stream of successes and failures? This is the promise and the power of reinforcement learning, or RL. It's a branch of machine learning that formalizes this natural process of learning through trial and error, enabling a computational agent to figure out how to achieve a goal in a complex, uncertain world. This makes it fundamentally different from the other major paradigms. Supervised learning is like a student studying with a complete answer key. Unsupervised learning is like a detective sifting through evidence to find hidden patterns. Reinforcement learning is different. It's not about classifying data or finding patterns. It's about learning to act. It's about creating a strategy to win. Today, we deconstruct this revolutionary idea. We'll start with the simple, elegant feedback loop at its heart, a conversation between a learner and its world. We'll explore the fundamental dilemma every learner faces: stick with what you know, or try something new. We'll then journey back in time to uncover RL's surprising dual origins in behavioral psychology and rocket science. We'll witness its coming-of-age moment with DeepMind's AlphaGo, a machine that taught itself to defeat the world's greatest Go player. And finally, we'll see how RL is already quietly shaping our daily lives. The philosophical shift that RL represents cannot be overstated. For much of its history, machine learning has been about pattern recognition. We build systems that can identify a cat in a photo, transcribe speech, or predict customer churn. These are incredibly powerful capabilities, but they are fundamentally passive. They analyze the world as it is presented to them. Reinforcement learning, however, is about creating autonomous, goal-seeking agents. It is the first truly computational framework for what it means to have a purpose and to learn how to achieve it. The goal is not simply to be correct in a single prediction, but to be successful over a sequence of decisions. This requires a dynamic interaction with the world, where an agent's actions influence the very data it will see next, creating a closed feedback loop that is the hallmark of true agency. To truly understand reinforcement learning, we need to break it down to its most essential components. At its heart is a simple, continuous conversation. Let's use a simple scenario. You're teaching a dog to fetch a ball. This simple interaction contains every core element of an RL system. First, we have the agent. This is the learner, the decision maker. In our analogy, it's the dog. In the world of AI, the agent is the algorithm we are training. Whether it's a game-playing bot or a robotic arm, the agent's entire purpose is to learn a strategy to achieve a goal. Next, there's the environment. This is the world in which the agent operates and with which it interacts. It's everything external to the agent. For our dog, the environment is the backyard, the grass, the fence, the location of the ball. For a self-driving car, the environment is the road, the traffic, the pedestrians, and the laws of physics. The environment defines the rules of the game. At any given moment, the agent needs a snapshot of the world to make a decision. This snapshot is called the state, often denoted as a capital S. The state is a complete description of the environment that is relevant to the task. For the dog, the state could be its own position, the ball's position, and its velocity. For a chess-playing agent, the state is the exact position of every piece on the board. The state is the sole piece of information the agent uses to decide what to do next. Based on the current state, the agent makes a choice. This choice is called an action, denoted as a capital A. The set of all possible actions is the agent's repertoire of behaviors. The dog can run, sit, bark, or pick up the ball. The chess agent can move its pawn forward, or its knight in an L shape. The agent's job is to learn the best action to take in any given state. Finally, and most importantly, after the agent takes an action, the environment responds with feedback. This feedback is the reward, denoted as a capital R. The reward is a simple scalar signal, a single number, that tells the agent how good or bad its last action was in the context of its goal. When the dog successfully brings the ball back, you give it a treat and verbal praise. This is a large positive reward, perhaps a +10. If the dog runs off and starts digging a hole, you might say no, which is a negative reward, a -1. If it just sits there and does nothing, the reward is neutral, a 0. This reward signal is the only guidance the agent receives. It's the bedrock of the entire learning process. These 5 components, agent, environment, state, action, and reward, are locked in a continuous loop. This cycle is the engine of learning in RL. Let's trace this loop, moving from our dog to a classic computational example, Pac-Man. First, the agent must observe the state. The loop begins. The Pac-Man agent observes its current state. Let's call it S sub t. It's at coordinate 5,10 on the map. A ghost is approaching from the left, and a valuable power pellet is located 1 square to the right. This complete picture is the state. Second, the agent must choose an action. Based on its current internal strategy, the agent must choose an action. A sub t, given the state, moving right seems like a good idea. The agent selects the action move right. Third, the environment responds. The agent executes the action. The environment then transitions to a new state, s sub t plus 1. Pac-Man is now at coordinate 6, 10, and the power pellet is gone. The environment also provides a reward, r sub t plus 1. Eating a power pellet is a highly desirable outcome, so the environment might return a reward of plus 50. Fourth, the agent learns. This is the crucial step. The agent receives the new state and the reward. It uses this information to update its internal strategy. The core of this update is a simple but profound realization. The last time I was in a state with a ghost to my left and a pellet to my right, I chose to move right, and I received a big reward. Therefore, the strategy of moving right in that kind of situation is better than I thought. I should increase the probability of doing that again in the future. This loop repeats thousands or even millions of times. Through this relentless process of trial and error, observation, action, and feedback, the agent's strategy gradually improves. It learns to avoid ghosts, seek out pellets, and ultimately, to win the game, all without ever being explicitly programmed with the rules of good Pac-Man strategy. This framework reveals something profound about how problems are defined in reinforcement learning. In supervised learning, the problem is defined by the dataset. The data, the images and their labels, the text and its translation, is the specification of the task. In RL, the problem is defined by the environment itself. The act of designing an RL solution for a new challenge, whether in finance or robotics, is primarily an act of environment design. One must first meticulously define what constitutes a state, what actions are permissible, and, most critically, what behaviors are rewarded. A poorly chosen state representation might hide crucial information from the agent, leaving it blind to the optimal strategy. And a poorly designed reward function can lead to perverse outcomes, a phenomenon known as reward hacking. This is where the agent finds a lazy or destructive shortcut to maximize the reward signal without actually achieving the intended goal. For example, an agent rewarded for cleaning up a mess might learn that the easiest way to get a reward is to first make a mess and then clean it up. The art and science of applying RL, therefore, is as much about building a high-fidelity, well-designed world for the agent to learn in as it is about the learning algorithm itself. We've established that an RL agent learns from rewards, but this raises a deeper, more complex question. In many real-world scenarios, the consequences of an action aren't immediate. Consider a game of chess. Sacrificing a pawn, a move that results in an immediate loss of material, a negative reward, might be the key to setting up a checkmate 20 moves later. How can an agent learn to make a decision that seems bad in the short term but is brilliant in the long term? This is the delayed reward or credit assignment problem. When the agent finally wins the chess game, it receives a large positive reward. But which of the dozens of moves that led to that victory was the crucial one? How does the agent assign credit for the final win to that clever pawn sacrifice made an hour earlier? The agent must be farsighted. It must learn to value actions that lead to the best possible future, even if they involve short-term pain. We formalize this idea with the concept of the return. The return, written as capital G sub t, is the total reward the agent expects to get starting from time t. To make the agent prioritize more immediate rewards over distant ones, which are often more uncertain, we introduce a discount factor. This is a small number, always denoted by the Greek letter gamma, that is between 0 and 1. Let's say we pick a gamma of 0.9. The discounted return is calculated as follows. The reward we get one step from now, r sub t plus 1, is taken at full value. The reward we get 2 steps from now, r sub t plus 2, is discounted by gamma. So we only add gamma times r sub t plus 2. the reward 3 steps from now r sub t plus 3 is discounted twice, so we add gamma squared times r sub t plus 3, and so on. The agent's true goal is to maximize this expected discounted return. To do this, the RL agent needs a brain, a way to represent its strategy and its understanding of the world. At the core of an agent's intelligence are 2 key concepts: its policy and its value function. The policy, denoted by the Greek letter pi, is the agent's brain, its strategy, its behavioral blueprint. Formally, a policy is a mapping from states to actions. It answers the question, given the current state of the world, what action should I take? The ultimate goal of the entire reinforcement learning process is to find the optimal policy, denoted pi star, which is the strategy that will accumulate the maximum possible reward over the long run. The value function is what the agent knows. It's the agent's intuition, its ability to judge a situation. A value function is a prediction of the total, cumulative future reward the agent can expect to receive, starting from a particular state. There are 2 main types. The state value function, V of S, estimates how good it is to be in a particular state S. Think of a chess grandmaster looking at a complex board position. They have a deep, intuitive sense of who is winning. That intuition is their internal value function for that board state. A state with a high value is one from which the agent expects to accumulate a lot of future reward. The action value function, Q of S, A, is even more specific and often more useful. It estimates how good it is to take a specific action A from a specific state S. It answers the question, if I'm in this situation and I make this particular move, what is my expected total future reward? With a good Q function, the agent's policy becomes very simple. From your current state, just calculate the Q value for every possible action and pick the action with the highest Q value. How does an agent learn these value functions? The mathematical magic behind this is the Bellman equation, named after the mathematician Richard Bellman. We won't dive into the deep mathematics, but the core concept is both elegant and intuitive. It provides a recursive way to define value, linking the value of where you are now to the value of where you could be next. Conceptually, the Bellman equation states, the value of your current state is equal to the immediate reward you get for taking an action, plus the discounted value of the best state you can get to next. This equation provides a consistency check. If an agent's value estimates are correct, they will obey the Bellman equation. If they don't, there is a Bellman error, and the agent can use this error to update its estimates and bring them closer to the true values. This iterative process of updating values based on the values of subsequent states is the engine that allows the agent to propagate information about delayed rewards back through time, solving the credit assignment problem. Armed with these concepts, we can now categorize the main families of RL algorithms based on what component, the policy, the value function, or both, the agent tries to learn. First, we have value-based methods. These algorithms, like the famous Q-learning, focus exclusively on learning an accurate action value function, Q of S, A. The agent builds up a massive table or a neural network that estimates the Q value for every possible state action pair. Its policy is then implicit and simple. In any state, just choose the action with the highest Q value. These methods are highly effective in environments with discrete, limited action spaces, like classic Atari games. Second, we have policy-based methods. These algorithms take a more direct approach. They don't bother learning a value function. Instead, they directly learn and optimize the policy, pi itself. The agent tries an action, and if the outcome was good, it adjusts its policy to make that action more likely in the future. If the outcome was bad, it makes it less likely. This approach is particularly powerful in environments with continuous or vast action spaces. For example, determining the precise amount of torque to apply to a robot's joint where there are infinite possible actions. Third, we have actor-critic methods. As the name suggests, this is a hybrid approach that combines the best of both worlds and forms the basis for many modern, state-of-the-art algorithms. An actor-critic agent has two distinct components. The actor is the policy. It's responsible for acting, for choosing which action to take. The critic is the value function. It doesn't act, it only critiques. It watches what the actor does and evaluates how good its actions were by estimating the value of the states it lands in. The critic then provides feedback to the actor, allowing the agent to learn more efficiently and stably than with either method alone. Let's look at the most famous value-based algorithm to make this concrete: Q-learning. Q-learning is a model-free approach, meaning the agent doesn't need to understand the rules of the environment. It just learns the Q values directly from experience. Here's how it works. We start by building a giant table, a spreadsheet. The rows are all the possible states. The columns are all the possible actions. Every cell, S, A, in this table will hold our current estimate of Q of S, A. This is our Q table. At the very beginning, we know nothing, so we just initialize this entire table to zeros. Now the agent starts living its life. It's in a state S. It needs to pick an action A for now. Let's just say it picks one. It performs action A, and the environment responds. It gives the agent a reward R and a new state sprime. Now we have one piece of experience, SAR sprime. We can use this single experience to update or nudge our Q table. We are going to update the old value in our table, Q of S, A. First, we calculate our target value. This is our new better estimate of Q of S, A based on this one experience. Our target is R plus gamma times the maximum Q value from the new state sprime. Let's translate that. The target is the actual reward we just got, R, plus the discounted best future value we can get from our new state sprime, which we look up in our current Q table. Now our old value, Q of S, A, is probably not equal to this new target. The difference between them is the error in our old estimate. We call this the temporal difference error, or TD error. It's the difference over time between our prediction and the new reality. We don't just replace the old value with the new target. That would be too unstable. Instead, we nudge the old value towards the target using a learning rate, denoted by the Greek letter alpha, a small number between 0 and 1. The final update rule is, the new Q of S, A equals the old Q of S, A plus the learning rate alpha times the TD error. And the TD error is the target, which is R plus gamma times the max Q value from sprime, minus the old Q of S and A. That's the entire algorithm. The agent just repeats this loop millions of times. Observe state, choose action, get reward and new state, calculate target, update Q table. This process is guaranteed to eventually converge. Its Q table will get closer and closer to the true optimal Q function, Q star. But I skipped a critical step. How does the agent choose an action? This brings us to the fundamental dilemma of reinforcement learning, the exploration versus exploitation trade-off. At the heart of any learning process, whether for a human or a machine, lies a fundamental and unavoidable tension. It's a strategic choice that must be made at every step. Should I stick with what I know works, or should I try something new in the hope of finding something even better? Let's use a human analogy. Imagine you've moved to a new city. After a few weeks of trying different places, you discover a restaurant that you really enjoy. The food is great, the service is reliable, and the price is right. Now, every Friday night, you face a decision. You can choose to exploit your current knowledge. You go back to your favorite restaurant, guaranteeing yourself a good meal. This is the safe, reliable option that maximizes your immediate expected reward. Or you can choose to explore. You could try that new, unknown restaurant that just opened down the street. This is a risk. It could be a culinary disaster. But it could also be the best meal you've ever had, a new favorite that is far superior to your current one. By exploring, you sacrifice a guaranteed short-term reward for the chance to gather information that could lead to much greater long-term rewards. This isn't just a philosophical puzzle. Too much exploitation is a recipe for mediocrity. The agent finds a strategy that works reasonably well and then sticks with it forever. It gets trapped in a local optimum. It will never discover the truly optimal strategy. Too much exploration, on the other hand, is chaotic and inefficient. The agent is constantly trying random actions and never takes the time to capitalize on what it has learned. Its performance remains poor because it rarely uses the best strategies it has already discovered. So how do we program an agent to manage this trade-off? One of the most common solutions is the epsilon greedy strategy. We introduce a small parameter, epsilon, the Greek letter epsilon, which represents the probability of exploring. The agent's decision-making process then follows a simple rule. Most of the time, with a probability of 1 minus epsilon, the agent behaves greedily. It looks at its Q table and chooses the action that it believes will yield the highest reward. It exploits its knowledge. However, with a small probability of epsilon, the agent ignores what it knows. It chooses a completely random action from all the possibilities. It explores. A typical value for epsilon might be 0.1, meaning the agent explores 10% of the time and exploits 90% of the time. Often this value is set to be high at the beginning of training, when the agent knows nothing and exploration is vital. As the agent gains more experience, the value of epsilon is gradually decreased, shifting the balance from exploration toward exploitation. The story of reinforcement learning is not a simple, linear progression. Instead, it's a fascinating tale of convergence, where two powerful but completely independent lines of scientific inquiry, one exploring the inner workings of the mind, and the other, the outer workings of machines, gradually discovered they were speaking the same language. Thread 1 begins not in a computer lab, but in the world of behavioral psychology. In the early 20th century, psychologists like B.F. Skinner were developing the theory of operant conditioning. The core idea was that behavior is shaped by its consequences. Actions followed by a desirable outcome, or reinforcement, become more likely to be repeated, while actions followed by an undesirable outcome, or punishment, become less likely. This is the biological blueprint for RL. An organism learns a successful policy for interacting with its environment through a system of rewards and penalties. For decades, this remained a powerful descriptive model. But in the latter half of the 20th century, a stunning connection was made. The key was a concept called temporal difference, or TD, learning, developed largely by Richard Sutton and Andrew Barto. At the heart of TD learning is the reward prediction error, or RPE. This is not just the reward itself, but the surprise associated with that reward. The RPE is the difference between the reward you actually received and the reward you expected to receive. This error signal is what drives learning. The truly remarkable discovery was that this abstract computational signal has a direct physical correlate in the brain, the neurotransmitter dopamine. Neuroscience studies reveal that the firing of dopamine neurons in the brain doesn't just signal pleasure, but specifically signals this reward prediction error. When a reward is better than expected, there is a spike in dopamine activity. This is a positive RPE, a learning signal that says, "Pay attention. That was surprisingly good. Update your values upwards." When a reward is exactly as expected, there is no change in baseline dopamine firing. No surprise, no new learning needed. And when a reward is worse than expected, there is a dip in dopamine activity. This is a negative RPE, a powerful signal of disappointment that says, "That didn't work out as planned. Update your values downwards." This discovery was profound. It suggested that our brains are, in a very real sense, implementing a form of TD learning. While psychologists were studying pigeons, a completely separate community of engineers and mathematicians was tackling a different, though structurally similar, problem. This was the field of optimal control theory. Born from the needs of aerospace and industrial automation, optimal control is concerned with finding the best possible way, the optimal policy, to operate a dynamic system to achieve a goal. How do you fire a rocket's thrusters to guide it into orbit using the minimum amount of fuel? These problems, like RL, are about making a sequence of decisions over time to optimize an objective. Both fields are built on the foundation of the Bellman equation. They were using different vocabularies. Control theorists spoke of controllers, plants, and minimizing cost, while AI researchers spoke of agents, environments, and maximizing reward. But the underlying mathematics was identical. The figures who are most credited with weaving these two threads together into the single coherent field we now call reinforcement learning are Richard Sutton and Andrew Barto. Through their collaborative research, and most importantly, their seminal 1998 textbook, Reinforcement Learning, an introduction, they created a unified framework. They took the trial-and-error concepts from psychology, grounded them in the rigorous mathematical language from optimal control, and presented a clear set of algorithms. In 2024, their profound contribution was recognized with the A.M. Turing Award, often called the Nobel Prize of Computing, cementing their status as the founding fathers of modern reinforcement learning. For decades, the ancient Chinese board game of Go stood as the grand challenge for artificial intelligence. It is a game of profound strategic depth. The number of possible board positions in Go is greater than the number of atoms in the known universe. A brute force search, the approach that had conquered chess, was simply impossible. Go was seen as a bastion of human creativity and intuition. That all changed in March 2016 when a computer program developed by Google DeepMind, named AlphaGo, sat down to play a 5-game match against Lee Sedol, a South Korean master widely considered the greatest Go player of his generation. The result was a watershed moment for AI, a 4-1 victory for the machine. AlphaGo didn't just win. It played with a style that was described as creative, beautiful, and at times utterly alien. How did AlphaGo achieve this feat? It was a brilliant synthesis of RL concepts with the deep neural networks we'll be covering soon. At its core, AlphaGo was a sophisticated actor-critic system, augmented with a powerful search algorithm. Its actor was a deep neural network called the policy network. Its job was to look at a board position and predict the most promising next move. Crucially, this network was first trained using supervised learning on a massive database of millions of moves from expert human games. This process, known as imitation learning, gave AlphaGo a strong starting point. It learned to play Go by first mimicking human grandmasters. Only after this was the policy network refined using reinforcement learning, by playing millions of games against itself. Its critic was another deep neural network, the value network. This was AlphaGo's intuition, its V of S function. Its sole purpose was to look at any given board position and evaluate it, outputting a single number, the probability that the current player would go on to win the game from that state. This allowed AlphaGo to assess the long-term consequences of a move without having to simulate the game all the way to the end. Finally, AlphaGo used a Monte Carlo tree search, or MCTS, for each move. It conducted a massive look-ahead search, exploring thousands of possible future game sequences. The policy network acted as a guide, pruning the search tree toward promising moves. The value network then evaluated the board positions at the end of these simulated branches. This combination of deep learning for intuition and tree search for deliberation was unstoppable. As revolutionary as AlphaGo was, it stood on the shoulders of human giants. Its initial knowledge was derived from a vast dataset of human games. This led to the next and perhaps more profound breakthrough, AlphaGo Zero. AlphaGo Zero was designed to learn tabula rasa. From a blank slate, it was given nothing more than the basic rules of Go. It was not shown a single human game. Its learning process was pure, unadulterated reinforcement learning through self-play. Starting from completely random moves, it played games against itself. After each game, it used the outcome to update its neural network, making it a slightly better player. This new, slightly stronger version then became its own next opponent. The results were astonishing. In just 3 days of self-play, AlphaGo Zero surpassed the abilities of the AlphaGo version that had defeated Lee Sedol. In 21 days, it reached the level of AlphaGo Master, the version that had defeated the world's top-ranked player. After 40 days, it had become arguably the strongest Go player in history. Most importantly, AlphaGo Zero rediscovered thousands of years of human-developed Go strategy, and then went on to invent entirely new, unconventional strategies that human experts had never conceived of. This was not just a better game-playing program. It was a proof of concept for a new kind of scientific instrument, one that could generate knowledge. While mastering ancient board games is a spectacular demonstration, the true measure of a technology is its impact on the real world. RL is rapidly moving beyond games to optimize complex, dynamic systems. Robotics is one of the most natural domains. A robot is an agent that must learn to interact with the messy, unpredictable physical world. Companies like Boston Dynamics integrate RL to train their robots to walk, run, and balance. The agent, controlling the robot's motors, learns in a simulated physical environment. It receives positive rewards for moving forward without falling. After millions of simulated trials, it develops a robust policy for movement that is then transferred from the simulation to the real-world robot. This is also used for robotic manipulation, training arms to grasp objects of any shape or size in a warehouse. A significant challenge here is the simtorial gap. A policy learned in a perfect simulation may fail when faced with the subtle differences in physics, friction, and sensor noise of the real world. Bridging this gap is a major area of research. You also interact with RL every day. When you browse Netflix or YouTube, you are interacting with systems shaped by reinforcement learning. The problem of recommendation is a sequential decision-making problem. The goal is to recommend a sequence of items that maximizes your long-term engagement. At Netflix, a form of RL is used to solve a specific problem. For any given movie, which piece of promotional artwork is most likely to entice a particular user to click? The context is everything Netflix knows about you. The action is showing you one of several different images. The reward is whether you watch. By continuously exploring and exploiting, the system personalizes the visual presentation of the entire catalog. YouTube uses full-fledged RL methods to model your entire watch history as the current state. The agent then learns a policy to select the next video to recommend with the goal of maximizing total session watch time, leading to more satisfying viewing sessions. Finally, RL is a powerful tool for business optimization. In algorithmic trading, RL agents are trained to make buy, sell, or hold decisions. The state is a complex representation of market data. The actions are trades, and the reward is profit or loss. In supply chain management, RL agents learn optimal policies for reordering stock, balancing the cost of holding inventory against the risk of stockouts. This is also the technology behind the optimization of robotic fleets in large-scale warehouses, such as those operated by Amazon, where RL agents coordinate thousands of robots with maximum efficiency. We've journeyed from the simple act of a baby learning to walk to the complex, world-changing intelligence of AlphaGo. We've seen that reinforcement learning is more than just another technique. It is a fundamental framework for creating goal-directed intelligence. But as with any powerful technology, the path forward is not without its obstacles. The field of RL faces several grand challenges. Perhaps the biggest hurdle is sample inefficiency. RL algorithms are incredibly data-hungry. They often require millions or even billions of interactions with an environment to learn an effective policy. While this is feasible in a fast simulation of a board game, it is completely impractical, expensive, or dangerous in the real world. You cannot teach a self-driving car to avoid collisions by letting it crash 10,000 times. The second challenge is reward engineering. The entire learning process is guided by the reward signal. The challenge of designing a reward function that perfectly captures the desired outcome without creating unintended loopholes is a deep and difficult problem. We already mentioned reward hacking, where an agent finds a clever but undesirable way to maximize its score. This is not just a technical issue, it's a philosophical one about how we align machine goals with human values. Finally, there are critical challenges in safety and ethics. How do we guarantee the safety of RL agents, especially during the early exploration phase, when their behavior is essentially random? And if an RL agent learns from an environment that contains historical human biases, such as in loan applications or hiring data, it can learn to replicate and even amplify those harmful biases. Despite these challenges, the future of reinforcement learning is incredibly bright. The very same techniques that were honed to master the game of Go are now being pointed at some of humanity's most complex and important problems. We are at the beginning of a new era where RL can be used as a tool for scientific discovery and large-scale optimization. But we've also just hit a wall. I've been talking about a Q-table, a giant spreadsheet with one row for every possible state. This works for a game like tic-tac-toe, but it completely and totally fails for the real world. What is the state of a self-driving car? It's the combined data from cameras, radar, and lidar. The number of possible states is, for all practical purposes, infinite. You cannot build a table. You cannot store a Q-value for every possible video frame. This is the problem of continuous or high-dimensional state spaces. The Q-table, our tabular method, breaks. We need a way to generalize. We need a thing that doesn't store billions of Q-values, but can predict the Q-value for a state it has never seen before based on states it has seen. We need a function approximator, and the most powerful, flexible, and effective function approximator ever discovered is the artificial neural network. This is the bridge. We've reached the limits of what classical machine learning can do. To solve problems with the complexity of AlphaGo, robotics, and autonomous driving, we need to move from the lookup-tables of Q-learning to a new, more powerful architecture. This takes us to part 4 of our curriculum, diving deep into neural networks. We are going to leave the world of tabular methods behind and enter the world of deep learning, and we will start in our very next episode with the fundamental building block. We will deconstruct the artificial brain cell that started it all, the perceptron.
You've been listening to AI Deconstructed. Join us next time as we unpack another layer of the technology shaping our future. Until then, stay curious. Subscribe for more.